Get started. Okay. Before we jump into the lecture, is there any questions about anything logistical or about last week's lecture? Okay. See none. Okay. I just want to say a little bit more about BGP hijacking. I want to talk a little bit about how we try and solve the issue, and then we'll jump into a different topic. So just to remind us, let me sort of draw out the diagram again. So we have a user, we have a website, we use the example of Concordia. So the user has a home router, or sorry, a home network potentially. So there's a bunch of stuff that happens in the home network. ARP is the protocol that's used there. And then they're going to hit a gateway, which is given to them by their ISP. It's basically like your modem where the one end is coming in, it's the ISP, and the other end that goes out of it is your personal network. The ISP will sort of draw like this. So example might be Videotron. We call this in BGP, this is called an AS, autonomous system. Autonomous systems are just sort of big clusters of entities that control a large set of IP addresses and things like that. So what happens between? I don't know. There could be lots and lots of servers, and the IGP is going to be the protocol that's going to govern what happens here. Okay, and Concordia similarly. They'll have a gateway. And they're going to have their own AS. So Concordia's actual AS is called RISC. It's sort of like a government thing. And it's given, or it manages a bunch of universities' networks in Quebec. Again, IGP will govern sort of the routing that happens here. ARP will govern the routing that happens internally. And then the piece that we talked about last class, first off, the motivation why we're talking about this is I want to convince you that you can't assume that nobody's in the middle of your communication, okay? And even if you trust Videotron and even if you trust RISC, you can't necessarily assume that there isn't somebody else, some adversary that gets into it. They can try and get in here, they can try and get in here, they can try and get in here, they can try and get in here. I'm not going to go through all the permutations, but the one that we considered is what if they try to get in here? And so this is called BGP. And it's basically the protocol where different ASs find each other and they figure out which IP addresses are controlled by which ASs, and then they route it, okay? And the attack is, there's different variants on it, but the simplest one is pretty simple. It's just you become an AS and you start advertising some of RISC's IP addresses and saying they belong to you. And now there's a conflict because there's two ASs claiming the same IP space. And there's some tiebreaker rules, and the tiebreaker rules are not really set up with security in mind. So like the simplest one is if you have a more specific IP range, you're going to be preferred. And so if you want to grab some of Concordia's traffic or RISC's traffic, then you just advertise a more specific IP address, and now the tiebreaker comes to you. Okay? There's other ways of hijacking BGP, but that's the simplest one. Okay, how do we fix it? So let's say I want to fix it with cryptography. This is a crypto protocol course. Last class, in the first class, we walked through all these primitives that we saw in 6110. Of all those primitives, which ones do you think might help solve this problem of trying to stop BGP hijacking somehow?
Signature.
Okay, so digital signature, why do you think?
Why? Because they have to match it. Like if it's coming from a authorized source or something, they have to match the signature. If the signature matched, then they allow this prefix. Otherwise, no.
Okay, so digital signatures, basically what we can do is we can say who specified pieces of information. So we can have identities attached to the information. Okay, that sounds promising to me. Is there anything else that anyone might think of using? Okay, so some sort of key agreement, key exchange. So maybe the two ASs could do a key agreement and then they would be able to talk to each other. That seems reasonable as well. Anything else? Sorry, is the certificate? Yeah, so that is a signature. It's a signature on a specific kind of message. It pertains more to the message itself, but the cryptography that's involved in a certificate is a signature. So that sounds good too. Anything else? What about encryption? Do we need encryption here?
Kind of MAC.
Okay, so MAC. So again, some things deal with confidentiality, some things deal with integrity. Does this look like an integrity problem to you, or does it look like a confidentiality problem? Okay, so I'm hearing both types of answers. Let's start with integrity. So integrity would be that we know sort of who's saying what. Okay, that does seem important here. Confidentiality would be, I don't know who controls a particular IP range. I'm going to keep that a secret, right? The problem with that here is that you need to know, if you want to route the information, you have to know where you're routing it to, and you have to know who's the recipient of that route. So confidentiality here doesn't add anything, okay? So it's strictly integrity. So of the integrity primitives, we have MACs, we have signatures. Key agreement, you can say, is sort of this pre-step to setting up a key for one of those two things. Okay, so what we're going to use here are signatures. That's going to be the solution. And certificates as well, more specifically, but let's start with digital signatures. Okay, so first off, I'll give you the name of the protocol. So it's called RPKI. Whoops. So the R stands for resource, just a sort of generic name. And PKI is a concept that we'll see a lot. It's called public key infrastructure. And it's basically, you can think of it as, how do I figure out whose public key is whose? Or I know a person, but I don't know what their public key is. How do I figure that out? Okay, who's signing what? What are the things that we might sign, and who are the people that might sign them, and how do you think this might actually do something to help in this case?
The person requesting, yeah.
Okay, so it's going to involve keys. So that's going to be the person who signs. So remember, a signature is, the signing part is done by somebody who has a key, a signing key, and then everyone else can verify that that was signed by that person. So without going into the details of a signature, just think of it as, now you know where a message came from. Okay, is it enough just if ASs start signing their IP prefixes? So they're all advertising, yeah.
Sorry, I want to ask.
Yeah.
Is it possible to have something like a non-repudiation to know who did what, so you can always verify this came from?
Yeah, so this is a related kind of property. So we call it repudiation. So repudiation is like, I did something and I can't deny it. There's no great solution to repudiation because let's say I didn't do something. It's hard to prove it's like you're proving a negative. You're proving that something didn't happen. Normally, what the main thing for repudiation is you have logs, and then you have to have confidence that everything's getting added to the logs. You can maybe add signatures to the logs so that things can't get modified, right? And then what you can say is it wasn't logged. That's your evidence that it didn't happen, kind of thing. Yeah. So that's yeah. Okay, if we just have signatures and ASs sign things, it doesn't solve the problem because, again, the problem I have isn't that, for example, last time we had the example of Pakistan Telecom, right? Everyone knows it's them. They're the ones that are advertising this IP range that belongs to YouTube, okay? If I add signatures, it's just like now I'm extra sure it was them as opposed to someone else, but it doesn't stop the traffic from going to them. YouTube's traffic from going to them, okay? So signing just takes care of who said what. It doesn't really solve the problem, yeah? So I need a new idea.
What if you bring in a trusted third party?
Okay.
Like a mediator between, like to kind of monitor the traffic. So for example, if Concordia says, let's say 132 bits, anything 132, blah, 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 comes to Concordia, they ensure that like that kind of gets, followed to an extent. So if anything suspicious happens, they kind of like look into it and maybe redirect it or whatever.
Okay. All right, good. So let's play with that idea. So let's say we have a trusted third party. I have the name of a trusted third party. So a lot of internet registration stuff is overseen by an organization called ICANN. And then ICANN is split up geographically. So the sort of North Central American so first off, there's a global sort of thing. This is more like the organization, and then there's an authority called IANA, and then for North and Central America, it's called RN. And then other regions of the world will have their own subset. Okay, so if we were talking about RISC or Videotron, they would both be governed by RN as opposed to someone else. Okay, so now we have that trusted third party. They're perfectly positioned, right? They're the ones that we should trust. We already trust them for a lot of stuff on the internet. Okay, but now what are they going to do? So now we have them. What can they do for us? So they could do something active like monitor traffic and try and detect attacks. What I'd like to do is I'd like to stop the attack before it even starts. And by the way, the answer I'm looking for is very, very simple. It's not, it's not, don't think it's some big elaborate thing. Okay, identify what?
Identify the entity.
Okay, so that's right. So which entity and what are you identifying?
If I'm a user, for example, if I'm Concordia, I have an identity which I have in Concordia. It's registered to my either cloud or my local repository that these kind of identity is registered with Concordia only. And then if anyone with that identity assigned can come to this network, you already are in the secure, you already in the registered entities or your IPs or your number.
Okay, so let's start with the first thing. So IDs, can we give, in this case it's AS to AS, so I'm going to give all the AS's identities. So that is true. So we have what's called an ASN, AS number, and this is unique identity for every AS. Who do you get it from? You get it from ARAN in North America. Okay, so this is who you're going to get that identity from. Okay, so now I have a way of identifying everything. Then I kind of lost the second thought, but what can we do with it now? So now I have a trusted third party, and all the ASs have identities. I have the capability of doing a digital signature. So how do I put that together? Who signs what, essentially?
So let's say if I'm trying to approach Concordia.ca,
Yep.
I'll be approaching the IP address.
Yep.
And basically if we are doing the three-way key exchange, then I'll be sending the digital signature key to Concordia.ca.
Okay, so let's just fast forward through that whole handshake thing. So now you have some keys or something, but what are you going to do with that then?
That's when the encryption has happened, and then we can start sending the messages back and forth.
Okay, so I can send a message now, and I know who it's coming from and where it's going. But how does that help me? Like in this case, I could establish a connection to Pakistan Telecom, and they'll say I control YouTube's IP addresses. But I have that secure connection, so now everything's encrypted and signed. So I'm happy, but it doesn't stop me from sending my traffic there instead of to YouTube, right? Yeah.
Well, since like the third party already knows everybody involved,
Yeah.
trying to send and receive a message, why don't they just handle the whole transaction? Like that way they ensure it gets to where it needs to get to without having like to go to the wrong person or wrong address, since they already know, okay, let's say Pakistan is trying to send something from Pakistan to Concordia, they don't need to send it to Google or YouTube, they already know where it's going.
Okay.
So
Okay, great.
it's impossible for them to.
Okay, so what we could do, what you described is a valid solution. It's not the solution that we use, but it's a different PKI, is we could have what's called a key directory. Actually, I'm going to just call it a directory, not a key directory. And basically, it would have entries like, here's an ASN, and here's their IP prefix. Yeah? And it would just have a big database of what the IP prefix is. So this would be hosted, say, by RN. They put up a server. And so what I do is I want to send it to Concordia's IP address. I go to RN and say, okay, here's the IP address. And they say, okay, this is the ASN that covers that IP prefix. Okay, that works. That's a valid solution. The only problem with it is performance. So ASN has to now, or RN, sorry, they have to answer basically every IP, everything that gets routed, like basically every packet that goes to a unique IP, they're answering where it's going, and they're not going to be able to keep up. Okay, so what we'd like to do is we'd like to take that directory and sort of give it to the people. Yeah, so we want the same property of like, this information belongs to RN. They're authoritative over it. Okay, but what I'm going to do is I'm going to give the records in the database to everyone, and then they can send it. As long as when I get a record, I know that that was RN's, what would be in their theoretical directory if they had one. Okay, so what's the name that we give for that concept? Okay, caching, no. URL, no. It was something that someone said earlier. Okay, it's called certificates. Okay, so this is what a certificate is, essentially. It's kind of like a directory, but it's just sort of split up. Okay, so what I do is I have an entry, like here's an ASN, and here's the IP prefix that they're authoritative over. And I run that I might include more information, but this is sort of the minimal information. I'm going to run that through a signature algorithm. Okay, and who's going to sign off on this IP prefix belongs to this ASN. RN. Okay, so RN's key, I'm going to just sort of do it as a subscript here. But that's the key. Okay, so what RISC will do is they'll go to RN, they'll say, you know I control these IP addresses, give me a signature of that. And so RN will sign it, and now you have kind of like proof that that's your IP address. Okay, so that's all a certificate is. It's basically information that binds usually two pieces of information together. Like I have an IP and I want to know the ASN that it belongs to. So it's always like I have two kinds of identifiers. Like I have a person and I have a key. I have a domain and I have an IP address. Whatever. And I want to know the mapping from one to the other. So a certificate takes two or more of those things, put them together, and then some party that we all trust that's authoritative over that is going to sign off on it. Yep. Okay. Questions? Yeah.
What's the difference between RISC and RN?
So RN is they control every IP address in North America. So they know who owns what IP addresses, basically. Yeah.
Sort of like a DNS?
Sort of. So like they. So DNS is a little different. DNS is about the domain name to the IP address. This is more IP address to like who actually owns it. So IP addresses are owned. Like someone owned, like Concordia owns, I had it in the last slide, I forget the block, but they have a certain block of IP addresses. Yeah.
This is not available to the public, right?
No, it is. Yeah. So if you go to whois or something like that, you can, that's, I guess, more for domains, but I think it might also cover IPs. There is some service that you could use to figure out
And
it.
the
Yeah.
certificate, I know you could view it on like Google Chrome or.
So that's
give you this information?
that's a different certificate. So this is so certificates in general are just things that bind things together. There's all sorts of certificates that we get. So BGP certificates would only be visible between ASs. They're the only ones that need to see it. They're probably servers. They don't really have a user interface. But anyways, that certificate information would get exchanged. What are some other examples of certificates? So what do you see in Chrome? Okay, so there's certificates for HTTPS, so that gives you a secure connection, and that's what we're going to talk about next. Any other certificates? Yeah, maybe. Yeah. What if you get a software update? How do you know it came from Microsoft?
It has a certificate.
Yeah.
But only the if you are, for example, I'm the IT into Concordia and I accepted and updated for the whole network. Only I can see, but not all the user probably can see the inner certificate of that software license.
Yeah, sure. Yeah, so whether it's going direct to the user or it's going to an administrator who gives it to the user, that code is going to come down with a certificate, and that certificate is going to prove, Microsoft will sign that code and say it belongs to us, it came from us. Okay, so this looks great. There's one small problem here. So let's say you're an AS and you receive one of these signed messages. Okay, so now you're happy. How do you verify this signature?
Using the public key.
Okay, so I need a copy of the message itself, which I'll have. So I won't be able to verify it without the message itself. And I'm going to verify it with the public key of RN. Okay. So they need RN's public key. Where do I get RN's public key? Let's say an adversary just signs it and says, I'm RN, I'm signing it with my key, but it's not actually RN's key.
Should have a directory for the keys.
Okay. So basically what we're going to do is we're going to assume that the computers that are on the network know the key and it's sort of hard-coded. So whatever software they're using, they have a copy of that public key. Okay. So we're going to assume it's hard-coded. And because there's not a lot of these, right? There's maybe 5 or 6 around the world. That's fine. I can keep track of 6 keys. And let's say like one of the keys gets lost and things like that. I'll learn about it probably directly, and it's a manageable number of keys. Okay. Now, if the number of keys is 2 million or 10 million, right? I'm not going to have 10 million keys hard-coded in my software. So, going to other kinds of certificates. If you have code signed, usually it's your operating system. So you already I have a Mac, my Mac knows Apple's key. Okay, that's not a problem. But HTTPS, it becomes a problem because there's 2 million websites, 6 million, 10 million websites that I can visit that have HTTPS. They're all going to give me a certificate. I can't know all of their keys. Okay, I could open up a website tomorrow, brand new. You had your computer, you bought it 2 years ago. Your computer from 2 years ago isn't going to know what my website is. They're not going to know that key. There's no possible way. Okay, so we're going to need a different solution eventually. But right now, this is so small scale that you can just get away with like hard coding keys. Okay. Okay, is this mandatory or not? So this isn't a question that you would necessarily know. So our PKI is not mandatory currently. But let's say you get 2 prefixes, one of them is signed and one of them is not signed. You automatically will prefer the one that's signed, even if the one that's unsigned is more specific or it would break any of the tiebreakers. Okay? So you will prefer, so clients prefer we call them announcements. Of IP prefixes. Okay, and what we see now in practice, for example, I mentioned there was an incident last year with Cloudflare, 2 years ago, I guess now, 2024. So that's something that was slowed down because of our PKI. So Cloudflare did have certificates, their AS had certificates, and so whenever they circulated those announcements and they were signed, people didn't misdirect that traffic. But not all the ASs knew about their signed announcements. So some of them were still receiving unsigned announcements and missending traffic. Okay, so it was a way that they were able to slow the thing down. And eventually when their signed announcements reached everyone, then the problem disappeared. Okay, so it sort of can slow down. In practice, it's useful even if it's not mandatory because it can slow down attacks. So I'll just write CF meaning, for example, like C, for example, Cloudflare 2024. Now there's other kinds of BGP hijacking. There's, I'll just say it doesn't prevent other kinds. And so the other main kind is called a route leak. I'm not going to spend a lot of time on this. I'll just give you the flavor of it. I'm just trying to think if it's better to explain it from Videotron or RISC perspective. Okay, I'll do it from RISC perspective. Okay, so we have a bunch of traffic. It's flowing into RISC. Traffic that, actually, I think it's going to be better to explain it from Videotron's perspective. let's say Videotron's trying to reach Risk. We talked about how they're like physically in the same location. There's a place in Montreal and they're in the same location. They probably have a direct wire between them. They don't really have to talk to someone else, okay? But if they're trying to reach some, say, a university in Singapore, they're not going to have a direct connection to it. And so what they're going to do is usually have an upstream provider. So this is somebody who kind of knows the rest of the internet. And then in addition, they'll have some people that they know direct. So they have direct relationships with. Okay, and so if Videotron wants to reach, I'll just write Google, even though Google is probably in that server room. Let's say Videotron wants to reach Google. They know that there's a route through their upstream provider. Okay, so they can go to the upstream provider in order to go to Google. What sometimes will happen is another AS will come. And they'll say, okay, I'm trying to reach Google. Is that you? Right? And Videotron should say, no, I'm not Google. I have my IP prefix and Google's is different. But sometimes Videotron gets confused and it says, well, actually, I know how to reach Google. I go through this upstream provider and then I reach Google. So yeah, I am on the path to Google. I'm on a path to Google. If you send me your Google information, I can get it to Google because I can go through my upstream provider, okay? And so whatever the upstream provider's telling Videotron, it's meant to be used internally. So Videotron's only supposed to use it for itself. It's not supposed to advertise it to its peers. But what can happen if it's usually a misconfiguration, it's called a route leak. What you do is all the paths that you know about internally, you start accidentally telling your friends about them. And then now all of a sudden, this person's like, okay, I can reach Google through you. And then all their traffic trying to reach Google starts flowing through you. Okay, so it's usually a misconfiguration error. But anyways, that's the other kind of thing. And here the problem is it's in the full route. It's still the case that Google controls a certain IP prefix, okay? That's what our PKI solves, okay? So this is still a problem because we're not signing the full route. We're just signing who controls what prefix. We're just signing that last step, okay? So anyways, BGP hijacking is still possible doing this kind of thing. And it's also happens accidentally due to this. And our PKI doesn't solve that particular issue. Okay, so this, by the way, I'll just put some tech terminology. We call this a VRP, a verified route, what was it? Payload. We actually call it a verified ROV payload. And then ROV itself stands for route origin verification. Anyways, this thing that's being signed, VRP, does not include a route. So we don't sign off on how to route information, we just sign off on who controls what IP addresses. Okay, so BGP, not a solved problem today. There is some work on it, and people continue. Now they're talking about, okay, can we put routes? Can we get signed authority, someone to sign over the routes and things like that? And so that's like sort of in flux as of today. So it's something that might be coming down the pipeline. Okay, that's all I wanted to say about BGP hijacking, unless there's any questions. Yeah. Sorry, it's route origin verification. Yeah.
The thing is, because this attack is on a larger scale than just the ARP poisoning that you would do on like a local network.
Yeah.
And plus, because of the certificates and all those other layers to it, you could easily be detected for doing this type. If you were trying to like attack somebody maliciously, not just by accident, like with the Pakistani thing.
Yeah.
So
That's correct. That's correct. It's not a sneaky attack where you're going to sort of get in the middle and people aren't going to notice or they're not going to figure out who you are.
yeah,
So it's more of a something like, usually it can also be, it's not necessarily that the ASs are bad. It could just be that their machines were compromised. So an adversary breaches an AS. Yeah. Then now they start routing the traffic through them. And until you are able to undo that, you have a window where you.
breaches it like by infiltrating it.
Yeah, exactly. Yeah. Yeah.
Like on the
Like
inside.
putting malware on it. Well, it could be an insider attack, so it could be someone with physical access, maybe an employee, but it could also be a remote attack where you just get malware on the machine and you're able to compromise it. Yeah.
And you said something about renting it, but that's also because you have a trace, right?
Yeah, so you could also try and rent them if there's people that would rent you out
But
their
then
ASs.
your information.
Yeah, so they're not going to rent it to you for the purposes of attacking.
Well, obviously.
Yeah, so there needs to be a pretense to why you need to do it and things like that. But yeah. Or you can go and try and go to RN and try and become your own AS if you wanted to. But again, you're gonna, once you do the attack, then you've burned your reputation, and so you won't be able to do the attack again. So but these attacks, when they happen, they're usually a couple days. So it's not something that gets fixed like in a few seconds. It's something that usually, I think most of these outages, like Cloudflare and the earlier YouTube one, took about 3 days to fully resolve, kind of. So you have 3 days of surveillance in the middle.
It's interesting. Like, what would stop like a foreign government that's like, hostile from even doing something like this?
Only reputation. So it's just that they don't want to burn it, or once they do it once, then people aren't going to trust them again.
Okay.
Yeah. Yeah.
The IANA, are they like neutral or like they are like biased towards like a particular country, region?
Yeah, so they're US based. They're they started, so ICANN, I think, was based in California. A lot of like the early internet kind of started like in Berkeley and like places in California. And so I think ICANN is located there. They're in international, so the I forget exactly what it stands for, but the I is, I'm pretty sure, international. But anyways, it is like pretty heavily influenced by kind of Silicon Valley style companies and things like that.
So they're biased.
Yeah. So neutral or not, depending on what you think of the United States. Okay, other questions? Okay, why did we go on this sort of rabbit trail? So A, it does have something to do with network security, right? B, we saw our first kind of crypto protocol. So we went out in the real world, we tried to apply cryptography. So it fits within the context of the course, period. But there was another reason why we were talking about it. What I want to do is I just want to motivate the idea that there could be an adversary in the middle of your communications, okay? So what we'd like to do is we'd like to move forward always under that assumption. So from now on, we're just going to always assume there's an adversary there. You can see one way that an adversary can get there, and there's lots of other ways that adversaries can get there, okay? So what can we do about that? Okay, so there's different contexts where we want to be able to communicate with someone. And again, we're always going to assume the adversary's there, okay? So for example, if I visit a website, that would be one example. Let's say I send an email, that would be an example. Let's say I do some authentication, like I sign on. Could be as simple as a password, but it could be like some more complicated single sign-on kind of thing. Then I want authentication there. It could be authorization. So I have a VPN, I go into Concordia, I want to prove to the server that I'm authorized to look at something. And so I'm going to have some piece of something that proves that I have access to that resource. Again, assuming an adversary is in the middle. So these are the kinds of protocols that we'll consider. Okay, so I'll kind of pick use cases where we tend to see protocols, and then we'll kind of look at what the protocols look like. I'm not going to spend a lot of time on the details of like, here's all the fields, and this is what all the fields mean, and there's 24 bytes for this and 3 bytes for that. I'm going to focus more on the cryptography and how it helps. Like, what are you actually trying to do at a cryptographic level? So it will cover more the crypto side. And then if necessary, if it's interesting for some reason to look at like those smaller details, we can certainly look at them. But I think for a lot of stuff, it's more just about the overall kind of setup. Okay, so the first thing, the first kind of protocol that's very useful to do is I'll just call it a secure tunnel. So we have a user, call her Alice. We have a server, call it B, so A to B. They want to send information back and forth. Now, because of BGP hijacking, ARP hijacking, all of that stuff, we're going to assume that there's an adversary, call them Eve, for eavesdropper, or Maori sometimes for, that gets more across the idea of malicious. So the adversary in the middle, they could just be passive, they could just read, but they could also be active, so they could change things that they see flowing back and forth, okay? But anyways, we're going to assume that we have an adversary in the middle. And what I like to do is this is an analogy, but I'd like to have kind of like a digital tunnel between myself and the server. And I'd like it to be the case that even though the adversary can sort of see the outside of the tunnel, they're not able to break into the tunnel and see the information that's passing through it, and they're not allowed to change the information that's going through it as well. Okay. Now, we can basically make this work using only the stuff that you've already seen. In fact, the stuff that you've already seen, it's probably there's probably 2 or 3 different ways that you could do this, depending on, you've seen enough to not just solve this one way, you can solve it 2 or 3 different ways, okay? When I say the stuff you've seen, I mean specifically the stuff that we reviewed from 6110. Hash functions, block ciphers, MACs, digital signatures, key exchange, public key encryption, PRGs, extractors, okay? But this whole thing isn't going to work unless if Alice knows something about the server that she's connected to. And so what I'm going to assume is somehow Alice knows the public key of the server. Okay, so somehow she knows Bob's public key. Okay, if she has that piece of information, she can make a tunnel to Bob using all the crypto stuff that we have. But of course, we should ask the question of how does she get Bob's public key? Okay. So I'll say preliminary assumptions. And the first is that Alice has Bob's public key. Okay. I'd like to know what you think about how this is, but I want to only ask people who have never taken INSE 6150 with me. Yeah. Yeah, sorry, what do you want the
background of the notes, the dotted background.
Yeah, the dots are too big, or you don't like the white, or
No, the dots are,
the dots are okay, yeah. You want them less bright or not as big? Oops. Sorry, I just forget where the setting is. I turn the dots on, but then it just helps me write straighter.
Maybe if you zoom out, it will be less visible.
Yeah, it's going to make everything small too, I think.
Yeah.
The templates, maybe.
Yeah, so I'm in the templates, but oh, here. Thanks. Okay. So we can do grids, or I can have it blank. It's just I'll write crooked. Blank. All right. Okay. Alice has Bob's public key. You've never taken INS 6150 with me. How does Alice have Bob's public key? Let's assume that Bob is a website. So I'm going to google.com or something like that. How do I have Google's public key? Or Concordia. Let's do Concordia as a better example. Okay, so there could be a directory, and it basically says, here's all the websites, and here's all the public keys. That is not the answer for the same reason it wasn't before. It is a possible answer. It works for small PKIs, like where you don't have a lot of public keys. But when you have, 10 million websites, it's too big. Yeah.
Isn't it the certificate?
Okay, it has to do with certificates.
Yeah, they're the certificates that are provided into your computer.
It's
Okay.
in the browser.
Yeah, so what will happen is Bob will send me a certificate, and it will say, I'm concordia.ca, and here's my public key. Okay? Now, does that solve the problem? How do I know, like, if there's an adversary in the middle, what's the adversary going to do? They're just going to swap out the public key for their own public key. Okay, now I have a secure tunnel to the adversary, not to the server itself.
Isn't the public key available for everyone on the net?
Yes.
Okay, what if Concordia, like I'll give the analogy of, it's a brand new university, it just started today, this morning, but I bought my computer 2 years ago. So I'm not going to know it yet. But it is a good guess.
Was pre-shared with the users?
So that won't work for the same reason. So like the website could be made, say I'm going to Concordia for the very first time, never been there before. So it wasn't shared with me.
We go to risk.
Yeah, so we could try and like use the ASs or something like that. So now we're getting to the idea that maybe there's a trusted party that's authoritative over this information. Maybe there's someone out there that knows it. Then they could sign it. So Concordia, remember, a certificate is information that's signed by someone else. Okay? So it is absolutely true that Concordia will present you a certificate. It will say, I'm concordia.ca. May or may not say, I'm Concordia University in Montreal. And it will say, here's my public key. It will be signed by someone. Okay? Who's that someone? Okay, so there's a certificate authority. So these are people that go around, their job is to sign these things. Okay? All right. How do I know the certificate authority's key? Okay, I wanted Concordia's key, so I got a certificate that was signed by a certificate authority. But to check the signature of the certificate authority, okay.
Something public.
Okay, so now the certificate authority's key will be in my computer. Okay, so I get a computer. It doesn't come with every key of every website, but it comes with a lot of keys that belong to certificate authorities.
You mean through the operating system?
Yep, so it can come one of two ways. So the operating system typically will have it, and some browsers will have it as well. So on Apple or on Mac, Apple will have it. It'll be in Key Store. On Windows, Windows runs it. On Chrome, I guess Google has a key store. And if I install Firefox, Firefox will come with its own store. And then it will default to that as opposed to my operating
And it
systems.
updates it every time you do an update.
The only way to change it is with a software update.
Yeah.
Yeah, so you can't change it, but it's not going to change very often. So these are going to be like keys that are known in my computer, and they're not going to change for 40 years.
Okay.
That's the idea of it. Yeah. Now there's a bunch of other complexities, like The organizations usually don't sign things directly with these keys. They sign another certificate, and that certificate signs another certificate, and then they issue my certificate. And how do the certificate authorities figure out what Concordia's key is? Right? They had to figure out somehow. That's why they signed off on it, right? And whatever method they use, why don't I just use it? Then I don't need a certificate authority. These are great questions, right? And so if you like those questions, come take INSE 6150, or you can watch the YouTube video, which maybe I'll cross-list it in the notes, but it's like 5 hours long, so it's not something you're going to want to watch for fun. But anyways, in that course I talk all about this PKI issue. Okay, so that's called PKI. How do we figure out whose key belongs to who? Yeah.
What if someone is trying to imitate the certificate authority themselves? Then won't that cause the trouble to?
Yep. So what if that is the attack I'm trying to prevent. So what if I go around saying I'm a certificate authority? Like, I'll give you the name of one, VeriSign. So I can go around saying, hey, I'm VeriSign, this is my public key, but it's really just me. Yeah. And so what will happen is I'll have to get that information signed by something that's in Apple's computer. So one of the certificate authorities are called root certificates, and they're ultimately it has to chain back to a root, otherwise I don't believe it. Yeah. Now, if I can trick a root into signing for me, right? Or if I just do it anyway and there's some sort of vulnerability in the software or a bug or something like that, then I can get away with it. So there's lots of stories of certificate authorities being breached, ways of getting them to think that you are Concordia even though you're not Concordia. There's lots of stories about like little stupid software bugs that people weren't checking and things like that.
So the operating system or the browser will have a list of certificate authorities that it accepts, right?
Yep.
So anything coming away from that is something that it won't actually accept it as a valid certificate?
Yep.
Authority?
Yep. So maybe worth, like, we can just take a peek at it. So for example, here I'm on Moodle, right? So what I do is they've changed sort of how it works here, but I go to connection security details. This is Safari. So it says Safari is using an encrypted connection to moodle.concordia.ca. Encryption with a digital certificate keeps information private as it's sent to and from the website moodle.concordia.ca. Then I can click on See Certificate. And so I'll see a bunch of information here that we'll talk about some of this stuff here. It's a little more than just here's Concordia and here's the public key. The public key is this value right here. Okay. So there's a bunch of other stuff. We're not going to concern ourselves so much with what all the other stuff is. In 6150, we talk about some of them and as it's relevant. But this certificate is signed by Amazon. So Amazon issued. They're the certificate authority for Moodle. And Amazon has a root certificate, and it's in my computer. If I want to see all the root certificates in my computer, again, specific to Mac, so this is system roots, and so you can see there's a bunch of certificates here. One of them will be that Amazon certificate that we were just looking at. Where is it? So it's here, one of these 4 certificates. I know that's kind of small to see, but okay. So my computer comes preloaded with all of these root certificates. That's a lot. You might be thinking, remember back in like a few minutes ago when we were talking about BGP and we just said, you know, this IANA or whoever like signs off on this information. Now we're talking about like 50 different organizations that could sign off on things. And they can issue certificates to other people to sign off on things too. And so the number goes to 200 or 600 depending on how you count. And if I can breach any one of them, this is probably the most important thing that we learned in 6150, but I'll tell it to you. Any certificate authority can sign a certificate for any website. Okay, so nobody knows that Concordia belongs to Amazon. If I show your browser a Concordia certificate that's signed by Secure Trust, no one knows that that's wrong. Okay, everyone has this Secure Trust root CA. It traced back to a root CA, so that's fine. Okay, so if I can breach any single one of these CAs or circumvent their issuing process, then I can get a certificate for any website. And now when I'm in the middle, I can basically make the tunnel end at me. Okay. Okay, so this is a big problem.
Is
Yeah.
it like all internet works like this, or is it only places that are like a Concordia, or it's like official organizations and stuff?
So any website can get a certificate that could make this kind of tunnel. So you don't have, you do pay for the certificate. Well, traditionally you paid, but now there's companies like Let's Encrypt that will give it to you for free.
That has to do with the HTTPS, though, right?
Correct. Yeah. So that's where we're going. So this protocol runs because we're using it to fetch websites. I'm talking about a secure tunnel for the internet for fetching websites, basically for fetching HTTP information. We call that HTTPS. But this concept of a secure tunnel is the same if you're doing a VPN or you're doing SSH. They all set up a tunnel. The cryptography looks basically the same, the way they set it up. It's just what you're sending to and from the tunnel is different.
So
Okay.
the
Yeah.
certificate authorities that you just showed, they were specifically for America region only?
So they're global. So they're yeah. So this is everything this is everything that Apple trusts that's in here. A lot of them are based in the U.S. for sure, but they are global.
But let's say if I go to Germany,
Mm-hmm.
and then will I have to get an update?
Good question. So I go to Germany. Do I have to do anything? Well, I'm bringing my computer. I'm not changing my computer at all. So yes. So I don't have to change anything. Yeah. So these are meant to work in any country. So every path to every server in every country should anchor back to one of these on the list. Yeah. Now some of these they'll sign certificates for CAs that operate within a specific country. So you might set one up in a country, then you might try and convince one of these root certificates to give you a CA certificate, and then you'll be that sort of middle certificate as well. Yeah. And so that's why the number is a lot bigger than the ones that you see here. Okay, other questions about this? Okay, so we're going to sort of set this thing aside, but I'll note that it's kind of like a big deal. Like there's a lot of attacks that just have to deal with Alice learning the wrong public key. It's like probably the easiest way to attack the protocol rather than trying to break into the tunnel. But for now, we'll maybe at the end I'll circle back and tell you a bit about it. But for now, we're just going to assume that is in place. Okay, I have a second question for you. What kind of key is PKB? We said it's a public key. How many primitives did we see when we went through all of them that use public keys? Okay, 3. Start naming them. Say it louder. Have confidence. Just shout it out if that's wrong. Okay, so encryption is 1. All right. Is this an encryption public key? Maybe, maybe not. Okay, signature. And certificate is a signature. It's a package signature, basically. Okay, these are the two. So we have encryption and signature. Yeah. There is key authentication, key agreement, but I didn't present it with signatures, but we'll see a variant with signatures. But anyways, okay. Which do I need to set up the secure tunnel, do you think? Do you think would you rather have an encryption key for Bob, or would you rather have his signature signing key? Okay, so encryption seems more intuitive, right? In fact, it seems like I can just start dropping messages into this and just sending it to Bob. Okay, so encryption will let us set up a secure tunnel, but it turns out signatures will as well. Okay, so there's 2 kinds of tunnels that you could perform. One of them will use encryption, and one of them will use signatures. Okay, if you were to compare the relative strength of the 2, the signature one is actually stronger. Okay, so we'll talk about why that is the case. But, okay, so when we use encryption, the protocol we use is called key transport. When we use signatures, the algorithm we call is key agreement. Or key exchange, but agreement sort of has, it's key exchange plus a signature, essentially. Okay.
That one we are using now.
Sorry?
I said, is key, like the key agreement, key exchange, what we are like using currently, like DH?
Yeah. So it is exactly DH. Yeah. Yeah.
Is it faster than encryption?
So the encryption is faster because you can. I'm going to write out the protocols. You'll see them side by side. DH requires a round trip. So I send something, they send something back. Now we're kind of done. But with the other one, I just send something and then I'm done, kind of. Yeah. So key transport is faster, but there's a security property that DH has that it doesn't have. That now we think is one of the most important security properties. And so in the latest versions of these tunnel protocols, we've actually gotten rid of key transport entirely. But anyways, I'm getting ahead of myself, but that's where we're going. Yeah. Okay, other questions here? Okay. Okay, so I'm going to break down how we form this tunnel. And the first thing I want to do is, for performance reasons, even though I have a public key for Bob, what I really like to do is I'd like to have a symmetric key. Okay, I'd like me to know a key and Bob knows the key and we both know the same key. I want this because it's way faster. Okay, public key encryption signatures, they're really, really slow. And so what I'd like to do is I'd like to use symmetric key encryption if possible. Okay, so what I'm going to do is I'm going to use the fact that I have public key encryption, and I'm going to use that just to try and get a symmetric key. Once I have a symmetric key, then I'm going to switch over and I'm going to do everything I want to do with the symmetric key. Okay, so at the very start, for a couple milliseconds, we're going to do a bit of public key encryption, and then we're going to switch to symmetric key, and then all the traffic to and from is going to be using symmetric key primitives. Okay. All right, so step one is we want to get Alice and Bob the same symmetric key. Assuming Eve in the middle. Okay, of all the primitives that we saw, does anyone have any idea how we might do this?
You mean you're talking about the public key, right?
So I know,
There's just one key.
so what I'd like to do is I'd like Alice and Bob to have, not the public, I want them to have a secret key that both of them know.
And only they know.
And only they know. And somehow they were able to learn what that is, even though Eve hears every message that gets sent back and forth.
Well, the Diffie-Hellman algorithm.
Okay, so there's something called Diffie-Hellman. We covered it, we called it key exchange, I think. So that's the algorithm that does this for us. Okay, so that's one. There's actually a way simpler way. Just look at it for a second and see if you can see it.
Through the tunnel?
So the tunnel isn't established yet. So the reason I'm trying to get these keys in place, then I'll have the tunnel.
Encrypting the key through the public key of the person you want to contact?
Okay, so Alice could just choose a symmetric key. She could encrypt it. She knows Bob's public key. Okay, so she could encrypt it for Bob and send it. Bob, if Eve's in the middle, Eve can't do anything about it. She can't decrypt it. Bob's the only person on Earth that can decrypt it. Bob decrypts it. Now he knows the key. Now they both know a key. Now they can start using symmetric key encryption. Okay, so these are the two worlds that we can live in. So the first is that simple protocol is what we call key transport. And it assumes that that public key that we have is a encryption key as opposed to a signing key. Generally speaking, for a lot of algorithms, a key, there's usually a type of encryption and a type of signature that uses the exact same key. So it might be RSA, that's the brand name of one signature and encryption scheme. It might be DSA, ECDSA, and then something like LGML. Or there's LGML is technically not quite enough, but there's other things. Okay. The other thing is key exchange or key agreement. And in this case, we're going to do some Diffie-Hellman thing, which I haven't described yet, but we will look at the details of Diffie-Hellman at this point. Okay, so what Alice does is she picks a key. This notation I'll just explain it. It looks complicated, but it's just saying something very simple. So this like E thing just means in, so it's an element of, and then this is specifying all the possible keys. What this is saying, it's a binary number, and it's 256 bits long, okay? So I have a key, it's 256 bits long. Every bit is either a 0 or 1, that's what makes it binary, and so that's where key's coming from. It's coming from that space. So Alice will choose this key. She'll choose it at random. So sometimes I'll write a little R above it. That just means at random. So it's not going to be guessable. Could you guess this key? Let's say you had some encryptions that were made under this key, right? Could you guess it?
No.
So what we hope is that the best algorithm you have for guessing it is to try every key. Okay, so you start at 0, you go 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, and you keep going, okay? Eventually you will hit the right key, okay? And when you hit the right key, you'll be able to recognize it because things will start decrypting, and now you've broken the encryption, okay? So in cryptography, nothing's impossible in practice. All the practical cryptography we use, there is a way of breaking it. And we tell you what the way of breaking it is. So I just told you how to break it. But all we do is we crank the complexity up so that even though you know how to break it, you're not going to be able to do it, okay? So how hard would it be to try every 256-bit string that's possible?
It takes so long.
Okay, so it would take a long time, so that's true. Like, what does that mean? Like 5 years, 10 years? Billions of years. So it is literally like billions. It's more like we're talking like the lifetime of the universe kind of thing. Okay. So how many possible keys are there? So it's 2 to the 256. That's the number of keys.
Is that the maximum amount? Because it's an element of that. So.
Yeah. So it could if you count every bit could be either 0 or 1. So you have two options.
Yeah,
If it's 2 bits, you go 2 times 2. Here we go 2 times 2 times 2 times 2. If it's 256 bits, we go 2 times 2 times 2, 256 times, which gives you 2 to the 256. Yeah? Okay, so we take the number 2 and we double it 256 times. Can anyone tell me something in the universe that's sort of close to this? Okay, so the number of atoms in the universe is it's higher. It's I looked it up because it's an analogy I often use, but it's about 2 to the 62 or something like that. 262. 2 to the 262. Yeah. So this is less. I like to say it's just a little bit less because it's pretty close. But because every time this number goes up by 1, you double it. It's actually a lot less because you're having it like 10 times. Okay. But if you think of the number of stars in the universe, like not just in the galaxy, not the stars that you look at and see when you look in the sky, but like in the whole, not in the Milky Way, but like in the whole universe, that's estimated to be a lot less than this. That's estimated to be about 2 to the 230. Okay, so this is more than the number of stars in the universe based on estimates. Okay, so you're not going to be able to try them. Even if you took all the computers in the world, including all the supercomputers, and you were able to run them for the lifetime of the universe, you're not going to find this number using that mechanism. Okay, what if you have a quantum computer? Well, if you're just searching here, a quantum computer is not going to help you either. Okay, it might make it like half, or I think there is an algorithm called Grover's algorithm that I think it takes a root of this, so it would be like 2 to the 128 instead of 2 to the 256. But anyways, it still would take a long time to do, and we don't have quantum computers, and no, they're not fast even if we do. Okay, that's fine. Okay, so what do? So all I do is I take my key, I run it through encryption. I use Bob's public key to encrypt. I get a ciphertext. And then what Bob does is he decrypts the ciphertext. He uses the secret key. So I'll write SK Bob here. That just means secret key Bob. And he gets back K. Okay, now we're done. We both have K. Now we can do whatever symmetric key encryption we want. Okay. All right, there's another algorithm called key agreement. Now, this is something I don't want to go into detail. So if you haven't taken 6110, you're not really going to understand this, but I'll show it to you anyways. It's pretty simple, and I'll tell you kind of why it works. What we're going to do is we're going to use some math. It exists in a certain kind of group. And what Alice is going to do is she's going to choose a random, kind of like a key. I'm going to call it A. So she chooses it at random. And she chooses it as an integer between 0 and some prime number. I'll write it as Q. And Bob's going to do the same thing. And what Alice is going to do is she's going to raise it to the power of G. She's going to take some generator G. So G is going to be something that's public. So I'll put here public. So everyone knows G. Everyone uses the same G. When the IETF standardizes, say, HTTPS, they say, here's a G value, you can use it. And so all the browsers use it and everything like that. It's a public parameter. There's nothing secret about it. You could use a different one as long as Alice and Bob agree, but there's no harm in everyone using the same thing. Okay? And so what Alice is going to do is she's going to do G raised to the power of A, but this isn't going to be just straight integer exponentiation. It's going to happen inside of a group. Okay? What a group is and all that stuff you're going to learn in 6110. I'm going to write it as mod P here, but there's other kinds of groups that you might do. Yeah, this is Diffie-Hellman. What Alice is going to do, what Bob's going to do is do the same thing. He's going to send back B. Okay. And what he's going to also send is he's going to send a signature on the two values, the value that he received and the value that he sent. He's going to sign. He's going to use his private key. I just want to give myself more space. So sign SKB. Whoa, what's going on here? And then what Alice will do is she'll verify that signature. So she'll take a copy of the message that she received. She'll take Bob's public key. This we can call sigma, that's the value here. She'll take the signature itself. She'll take Bob's public key. And hopefully that equals true. She'll check whether that equals true. If it does, then she knows she signed it. Okay. So we call this key agreement. The signature prevents, I want to talk a bit about why this sort of works in practice, okay? So there's a thing in math in cryptography that you're going to learn called the discrete logarithm problem. And it basically says that if I give you G and G to the A, it's infeasible to find A. Okay. Infeasible, again, doesn't mean impossible. It just means sort of like lifetime of the universe kind of thing. Okay. All right. Why?
But a quantum computer could do it faster.
Yes. So this particular problem is one that a quantum computer can do almost instantly if it was big enough to do this. Yeah. So the numbers we use here are pretty big. They're even bigger than this. They're like 2 to the 496 bits. 496 bits, which is 2 to the 496. But anyways, the A's and B's might be like 256 bits. Okay, so because of this, if the adversary's in the middle and they see G to the A go by, they can't pull A out. Okay, so they don't know what A is. If the adversary sees G to the B go by, they can't pull B out. Okay, that's what this discrete logarithm problem says. All right. If the adversary changes G to the A to, say, an A value that they choose, or if they change G to the B to a value they choose, they can do that. Nothing stops that. Okay? What you'll end up doing is you'll end up getting a key with the adversary. And so that's why we need the signature. So the signature, so actually I sort of misspoke, I missed something here. So you want to verify that the signature is correct, but you also want to check that the GA here is the actual GA that you sent. Okay? So is this the right GA, and is this the same GB that I received? Okay, then I believe that the adversary didn't change any of the values in the middle. Okay, now this is missing one piece still, okay, which is the actual goal. Alice was able to send this G to the A, and no one can get A out, even Bob. Bob doesn't know what A is here, okay? And Bob is able to send G to the B to Alice, and Alice has no idea what B is either. She's in the same position as the adversary. She can't pull it out, okay? What I said is I want two people to have the same key. Okay, right now, do they have the same key? No. One knows G to the A and one knows G to the B. Neither of them know A, or like one of them knows A, one of them knows B, but the other one doesn't know it. Okay, so how can I get them to get the same key? So say it louder.
Alice will take the Bob's key, like whatever Bob send, and multiply it with her key or raise it to her key.
Okay,
And
so
same thing we'll do.
okay, good. So even though this is like weird exponentiation, it's in this mod P setting and there's this whole discrete log problem, we can still do math. So the rules of multiplication and exponentiation still work the way that you would expect them to work. Okay, so what Alice will do is she says, I received G to the B from Bob. What I'm going to do is I'm going to raise it to the power of A. Okay, not send it, just compute this value. And what is this value? G to the A times B. Okay, all right. And here Bob is going to do the same thing. Okay, and so Bob is going to receive G to the A. He's going to raise it to the power of B. And what's that value? Is it the same value?
Yeah.
It is now. Okay, so now they've achieved the same value. Okay, so basically they take the thing that they don't know and exponentiate in the thing that they do know. Okay, all right. Can we use G to the AB as our key? Can we use that as a 256-bit key? So it's a shared secret, right? Is it random? If A is random and B is random, is G to the AB random? It is, okay? So that's another property. All right, so this looks good. There's only one problem, which is because, actually, can anyone tell me what the problem is that has taken 6110? Because otherwise you wouldn't know what the problem is.
The man in the middle can like take J to the power of E from Alice, keeps it, and generate out his own J to the power of A.
Yeah.
And then send it to Bob.
Yeah.
And then Bob sends his own J to the power of B. He keeps the one for Bob, generates another one, because Alice doesn't know what J to the power of A is, and sends it to Alice.
Correct. Yeah, so what you're describing is the man in the middle attack here. I won't draw it, but what the man in the middle can do is they can basically replace G to the A with an A that they, and a G to the B. But what happens here on the third line? So Bob will sign what the adversary sent, not what Alice sent, and then Alice will catch it. Yeah. So this is why, by the way, Diffie-Hellman, when you take 6110 and they say, here's Diffie-Hellman, they're going to show you lines 1 and 2, not 1, 2, and 3.
Yes.
1 and 2 is the simple version, the textbook Diffie-Hellman. It is not secure against a man in the middle for that exact reason. Yeah. What we have here is we have signed Diffie-Hellman or authenticated Diffie-Hellman, and that secures it against the man in the middle. Yeah. Okay, so the final piece is that G to the AB is still a weird number. It's not exactly a bit string, okay? There's a bunch of G values, and sometimes they're like points on an elliptic curve. Sometimes they're a subset of all the integers that are possible. It's random. There's 256 bits of randomness here because A and B were chosen randomly, okay? But it's not like a uniformly distributed random number, okay? So if I have a string that has randomness in it, but it's not a uniformly random string, can I convert it to one? Something that's uniformly random? So there was something that I showed you. Anyone remember the name of it? So pseudo-random is the opposite. That's where I start with something and I expand it. Here I want to sort of squish it. Extractor, okay? So what I can do is I can then say, okay, my key is going to be the extractor run on G to the AB. And extractors aren't secret. There's no secrets in them. It's just like a public algorithm. Often, including secure protocols like this, people use a hash function. Okay, so in HTTPS, now it's a little different how they do it, but in the earlier versions of TLS, as it's called, that extractor is just a hash function. So you can sort of think of that in your mind. Technically, it's not exactly a hash that you want, but people use hash functions. It's kind of like the Swiss Army knife of crypto, where you use it for a bunch of stuff that it's not necessarily designed for. And no one's been able to break it because they use a hash instead of a proper extractor. So anyway, so you can think of it as you just sort of hash it, and then you get out a key. Okay? So at the end of the day, both of these protocols are the same. They have the same beginning, which is Alice knows Bob's public key. They have the same ending, which is that they both end up with K. They know it, and the person in the middle does not know it. Okay? So there are two different ways of doing basically the same thing. Subtle difference in terms of security, but let's take a break. It's been a while. And then when you come back, I'll tell you what that difference is. Okay? So take 10 minutes. Okay, if everyone can take the seat. Okay, so we left off, I showed you two protocols. They achieve the same thing. What's the difference between these protocols? The only real difference in terms of like behavior is one uses a signing key. So this one, it's Bob's signing key that I know. And this is Bob's encryption key that I know. So if you're in a situation where it's like, I know Bob's encryption key, I don't know what his signing key is, then you have to use key transport, and vice versa if you just know the signing key. But if you know both, or the same key could be done with both algorithms, then you do have the choice between the two of them, okay? So generally what will happen in things like HTTPS, where you go to a website, is you used to have the choice. So they would give you a certificate and it would have an encryption key and it would have a signing key, and you can decide which of the two you want to do, okay? Now, over time, we phased out the first one for reasons that I'll talk about in favor of the second, but anyways, I will present it as if you have the choice, because in a lot of protocols you have the choice. Okay, if you're going to look at these two, which would you rather do? Would you rather do the left side or the right side?
The key transport.
Okay,
The left one.
all right, why do we like the left one?
Less computation.
Yeah,
Less
less
computation.
Okay, so we don't have a full round of communication. Okay, so for performance reasons,
I think the first one is doing good in the performance.
yeah. So KT I'll put as key transport, that's the first one. Is more efficient. Because it's just a one-pass protocol. Key exchange is a two-pass protocol. Okay, any other differences that you can see between these two? Okay, here's one that you might not think of. Let's say that I presented it as like going to a website. Okay, if I go to the website, is the website online? It is, right? Okay, but what if Bob is offline? Like, say this is more like an email or secure messaging or something like that. Okay, so what I want to do is I want to send a message to Bob, right? Do I need Bob online to do key transport?
No.
I don't, right? I can just pick the key, I can encrypt it, send it, so he has the ciphertext waiting there, it's cached, he's waiting for it, and then I can go ahead and start encrypting my messages for him as well. They're waiting there, he comes, he decrypts the key, and then he decrypts the messages, okay? So key transport works when Bob is offline. What about key agreement? Does that work if Bob's offline?
No, because it needs a reverse message. from-
Okay, so I need a reply
Yeah.
from Bob before I can make my key.
Yes.
Okay, so okay, so Bob is online in this case. Now, there is a kind of middle ground. What if Bob just sort of generates a bunch of these G to the B's and kind of like leaves them there? He's like, I'm going offline. You want to talk to me? Just grab one of my G to the B's, and then you can do this protocol, and then I'll get back to you when I do it. Okay. So in that case, I can do it. Okay. So in this case, I won't get the signature from Bob on G to the A because I didn't send him it, but I already know the G to the A anyways. So what I'll do is I'll get his signature on G to the B. I'll choose my G to the A and I'll start using it. And then when I send everything to Bob, if an adversary changes my G to the A, then Bob just won't be able to decrypt because it will be the wrong key. So I won't go through all those details. But anyways, what we could do is we could cache a bunch of these things. Okay, so there are some protocols. Signal is one where you message people. They might be offline. Okay, so messaging is one thing where you don't want to have them online. And so what you'll do is you'll get one of these cached Diffie-Hellman exponents, they're called, and you'll use that to form a key. And then when they come back online, and there might be a server that is online that will give you, so you can say, hey, give me one of Bob's G to the B's. And you kind of trust the server, but at the same time, Bob chose it and he signed it. So the server can't really lie to you anyways. And so that's sort of a middle ground as well. So Bob normally would be online, or it's also possible with like cached, sort of pre-computed. Yeah, G to the B values. So it's one way that we try and coerce key exchange into working offline. And later, like I want to cover Signal and some of those protocols as well. So hopefully we'll see this detail again later. Okay, any other differences that you can see between the two of them? Anyone who's taken 6110? No one? Yeah. Okay, so let's talk about that. So this is sort of closely related to what I want to say. Just let's work on this and then I'll get your answer. So expiration date, what does that mean?
The signature has a time limit.
Okay, so the signature could have a time limit on it. In this case, how fast does A and B do this? So if B's online, let's assume that B's online, it happens within milliseconds. Yeah? So you're close to something, but it's not really limited to time, but it has something to do with the passage of time. Yeah. Yeah.
Okay, I was going to ask now for the key transport, the key has to be kept, right? Like one private key is used to encrypt. So what happens if the key gets leaked for the key transport, all pass message is also forwarded. But for the key agreements, the keys are ephemeral, like they are deleted instantly after the handshake.
Okay. Okay.
So that makes it, I think that's why they call it forward secrecy, kind of makes it more secure, like your past messages are kind of secure, unlike the key transports where the past, once the private key goes, everything else that, like, that's when they keep it with that key also, like, it's,
Okay, so that's exactly the answer I'm looking for. So we'll go through the details step by step, but yeah. There's one other thing I want to squeeze in, just because it's like sort of a less obvious thing. But what if someone has a bad random number generator? We'll come back to the forward secrecy in a sec. If Alice has a bad number generator here, they're both kind of compromised, right? Here, as long as one of the two has a true A or a true B, the other one could have a compromise, and then the K will be truly random. Okay, so in key transport, only Alice, it's purely on Alice to choose the key. In key agreement, both of them choose the key as well. They both contribute randomness to the key. So Alice contributes randomness. And in key exchange, both. Okay, and so this is better in case Alice has a bad pseudo-random number generator. Okay, now let's go to the next one, which is this perfect forward secrecy property. Okay, so I'm going to pull out one thing that you said, and we'll try and build out what we're talking about. So you talked about keys getting compromised. Okay, so first off, what key are we talking about here? So there's two keys that are involved. Let's start, I'll lead you to the simplest one first, okay? Let's say that K gets compromised. Okay, so somebody learns what K is, all right? Can they break into the tunnel knowing what K is? So K is the key that we're going to use, like a block cipher key or something like that. We're going to send stuff back and forth.
Yes.
So yes, so if I know K, I break into the tunnel. It's actually the definition of what it means to break into the tunnel, basically, is to learn K, okay? Is there a difference between KT and K key agreement in terms of that. So there's no difference.
No.
Both of them output K, and it's actually what you turn around and do with K. But in both cases, if K is compromised, the protocol's over. Okay. Sorry, I just noticed that I said key agreement, not key exchange. So I'm going to just change these ones to. Whoops. Okay, what's the other key that's used in the protocol? So the public key, and it has a corresponding private key. So Bob's, who knows the corresponding private key?
Only each person.
So Bob knows the private key that corresponds to the public key.
Yeah.
Yeah, so that's Bob's public key. Is it Alice's public key or Bob's public key?
It's both of them.
It's only Bob's public key. This is also another thing I didn't explicitly say, but at the end of this, Alice knows who Bob is, but Bob doesn't know who Alice is. Okay, so what we're doing is we have sort of a one-way authentication where I have a tunnel to Bob, but Bob doesn't know he's talking to Alice. How does he figure out he's talking to Alice? We'll send some username, password, cookies, that kind of stuff. But anyways, and there are ways of changing it so that both parties have public keys. That's called mutual authentication. But maybe I'll put a bullet point later. Okay, so in both cases, it's Bob's public key. Bob has a private key. All right. Let's say you steal Bob's private key. Okay? What can you do if you steal Bob's private key? Let's say you're an adversary in the middle, and now you have Bob's public key. Are you able to break this protocol? So let's start with the key transport. You have Bob's public key now. What are you going to do if you're in the middle? I'm an adversary. I'm in the middle. I see C go by. What am I going to do? I'm going to decrypt it and get K out. Yeah? No problem,
Yeah,
right?
Don't you need the private key? For that?
That's what I'm saying. If I have Bob's private key.
Private.
Yeah.
Yeah, if you have that, you can decrypt.
Yeah, sorry, I might not have said it strong. So in both cases, what we're going to do is we're going to assume Eve or Mallory, the adversary in the middle, has private key Bob. Bob's private key. Okay, what about here? What can Bob do? Or sorry, what can Eve do with Bob's public key?
Well, without it, if it's the first or second stage, you can always kind of switch.
Okay, so what Bob can do is when Alice sends a true G to the A, he'll replace it with his own G to the A. When Bob sends back a G to the B, he'll replace it with his own G to the B. So Alice and Bob will they'll be both talking to Eve in the middle. And so that works. But what prevents that attack is this signature. But now I know the private key of Bob. So what will I do? I'll just sign, like whatever both parties are expecting, I'll sign it for them. Okay? So I'm able to intercept it. Once I sign it, then I'm going to have a K with Alice and Bob, and I'll have a K with Bob, and the whole attack will work. I just said that like kind of waving my hands around. I think it's complicated enough that maybe let's actually draw it out, just to convince you that it's the same. But I'll make the point. So they can intercept. If this is true, Eve can. I'll put it more colloquially. I'll just say break the tunnel. For both key transport and key agreement. So in other words, what I'm telling you is there's no difference. So they're the same. You don't prefer one or the other. Both of them break if the key gets compromised. It's pretty obvious looking at this why it breaks. It's a little less obvious looking at this to understand why it breaks. So I'll draw out what happens in that case. So we have Alice. In the middle, we have Eve. And then we have Bob. Okay. So what Alice will do is she'll send G to the A. Okay. What Eve will do is Eve will choose an A prime and a B prime that she knows. So Alice here knows A. Eve doesn't know A, she can't get A out. Okay? But what she'll do is she'll pass on to Bob G to the A prime instead. So that's her chosen A. Okay? What Bob will do is Bob thinks he's talking to Alice. He doesn't know there's someone in the middle. He'll pick a value B. He'll send G to the B. Again, Eve doesn't know the value B. Okay? But what she'll do is she'll pass on G to the B prime. Okay? All right. So far so good. Then what will happen? Then Bob will pass on a signature. And so he's going to assign G to the A prime and G to the B. If Eve passes the signature on to Alice, is Alice going to say that signature looks good? She'll say it's completely wrong. This G to the A value, this first value, it doesn't match what I sent. And the G to the B that you signed off doesn't match what I received. It's completely wrong. Okay? So that's why I need the key in the middle. So I need this key here. Then what the adversary can do is they can change the signature and they can sign what she's expecting to see, which is G to the A and G to the B prime. Okay? Alice will end up computing G to the A to the B prime, which equals G to the A B prime. So that's going to be Alice's key. Okay. Bob is going to compute a different key. He's going to take his G to the A prime that he received. He's going to raise it to the power of B. He's going to get G to the A prime B. So that's the key that Bob has. So Alice will encrypt things thinking they're going to Bob using this key. Bob's going to encrypt things or decrypt things that he receives using this key. What we need the adversary in the middle to do is know both keys. If she knows GA and GB, then she can switch the key in the middle. So something will come encrypted under key A, and she can encrypt it. She can switch it to an encryption for KB, send it on to Bob, and then back and forth. Okay? Can Alice get both of these keys? So she can. So Alice in this case knows G to the B. She received it. She knows her own A prime. So she can get G to the A prime B, which is the same key that Bob has. And on this side, she can do the same thing. She gets G to the A, raises it to the B prime that she chose, and she gets G to the A B prime, which is the same as KA, and it's the same thing that we have here. Okay, so it's a little less obvious why compromising that key. You have to do a bit of math to see it, but compromising the key is enough to destroy it. Okay, and that's what you should expect, right? Let's say it wasn't, then somehow you're able to talk to people even though you don't know their key, which sounds impossible, right? So this is sort of expected. Okay, okay. So there's no difference between them if you're able to compromise the key. Okay. But there is this thing called perfect forward secrecy. Okay, so can anyone tell me why there actually is a difference between the two? Yeah.
So, if, let's say that Eve gets to know the secret key afterwards, after it has been established, then it cannot get back the secret key.
Okay.
However, it could do that with the key transfer.
Okay, great. So let's pencil that in. So here what I'm going to say is Eve gets the secret key of Bob, but she gets it after the communication is done. Okay? And I'm also going to assume she has a copy of the communication. Okay, so she also has a copy Okay, this sounds kind of weird. What does that mean? You get the key later and you have a copy of the communication. It's pretty simple. I want to know what you're talking about. I can't break it because I don't have your key. Okay? The second best thing I can do is just record everything I'm seeing, even though I can't break it today. Maybe in a year I'll get malware on your machine or get a keystroke logger or whatever. I'll get your key. Then what I want to do is I want to go back because I stored all of your communication. I want to read all your past messages. Okay? So can I do that or not? So let's go through them one by one. If I write down C today, okay, I can't break it. I don't know the private key, okay, but I just write down C. And then these people start encrypting stuff with K. I write down all those ciphertexts. Now, a year later, I get private key Bob. Can I figure out what K is? How do I do it? Just decrypt it, and then I decrypt everything that was encrypted with the K. Okay? So I'll say Eve can break. Actually, I'll put it more specifically. I'll say Eve can compute. Okay. Who's an Eve in real life that might do this kind of attack? Okay, US government. They have huge data facilities. They just look like storage facilities. It's top secret. No one knows exactly what they're doing.
NSA?
Yeah, NSA. So probably what they're doing is they're just recording all encrypted stuff that they can find. And then if they get a quantum computer in the future, or they if there's an error in the algorithm or something like that, then they could break it and they could potentially use that information. Okay. Okay, so this is a realistic threat. It's something people are concerned about. What about key agreement? What happens in key agreement? So I'll put the algorithm up, stare at it for a bit, and try and tell me whether you can figure out what K is. If this whole communication happens, it's done, you recorded everything, now you have K. Now you have the secret key at Bob, are you able to get K? Okay.
You have to, like, each time they establish a connect, like an agreement, an handshake, it's a different. Alice can choose a different A.
So that is true. Yeah, every time you talk to Bob, like say you talk to Bob once a day, every day you're going to choose a different A and B.
So it's
But I'm going to write all of those down. Yeah.
Doesn't the discrete algorithm problem protect it?
So the discrete log problem prevents the adversary from getting A or B out. Yeah.
Like, if I don't know A and B later on, G to the power A and G to the power, I can know the signature if I have the signature.
That's right. So if I know the signature key, what can I do in the future? I can sign messages saying I'm Bob, right? I can do that in the future, right? Does that let me break the protocol in, looking at past communication? The fact that I can, no. So I need to be able to sign, I need to be in the middle, and at this step, in step 3 here, that's when I switch the signature, okay? I need the key at step 3 here. If I don't have the key at step 3, then they're going to set up a key, and I'm going to have no idea what it is. And I can impersonate Bob all I want in 5 years from now. I can't go back in time and make them set up the key with me in the middle knowing the signature, okay?
That's what I call forward secrecy.
That's what's called forward secrecy. So forward secrecy means that once you get past, once you get forward in time from the communication, like your session's over, if the key wasn't compromised, then you're secure forever. Assuming the discrete log problem is still hard and a bunch of things like that. Yeah? Okay. Does this protect against a quantum computer? It doesn't. So in that case, I'm not going to break it. This protects against me learning this value here. So I breach the server, I get SKB. With the quantum computer, DL doesn't hold anymore. So then I can just figure out what A is, and I can figure out what B is, then I can figure out what G to the AB is. Okay? So
This is a
yeah.
2-pass though, right? Because I know there's a 3-pass Diffie-Hellman, which is more secure than the 2-pass.
So there are different variants on Diffie-Hellman. We may or may not talk about
Okay.
different ones, yeah. Okay, so key agreement, Eve cannot compute K and break encryption. Okay, and note this is with SKB. Okay, so that's one very realistic threat, which is that you have your key, it's lying around on your computer, you're using it for a couple of years, and someone's able to compromise it at some point. Can they go and decrypt all your past communication? And so this doesn't happen. But with a quantum computer, I'm not going to try and get SKB. What I'm going to do is I'm going to just get, I can get A and B from G to the A and G to the B. And then I can break it as well. So it's just, some people sometimes confuse it and think, oh, forward secrecy, I'm secure against quantum computing as well. But in this case, you're not actually secure against it. Okay, but because you're breaking it a different way. You're not breaking it by stealing the key. You're breaking it by actually breaking the crypto itself. So forward secrecy applies just to the threat model if someone steals your key in the future. Okay, so all of that said, which of these two are better on balance?
Key agreement?
Yeah, key agreement. So most people think that's a real threat, right? People writing down your communication and then compromising your key in the future. Even though it's slightly less efficient, you don't really feel it, right? Like you're probably going to have a couple rounds of communication anyways, because you're usually talking about like what protocol do you want to run, what algorithm, what version, what encryption algorithms you want. And so everything ends up being like a three-way handshake anyways. And so it doesn't really make that much of a difference. And this is also better because A and B are both contributing randomness as well. So usually this is like some server, and Alice could be like an IoT device or something. So the chances that Alice has bad randomness is actually pretty high, but the server is probably more hardened, and it has a higher chance of having good randomness as well. So there's a lot of Alices in the world where they're going to have sketchy randomness. So we also like the idea of both of them contributing randomness as well. Okay, so that's so now. So we didn't really talk about the protocols that use secure tunnels, but I'll say that an application of a secure tunnel. So they're used for a lot of things, this basic idea, but an application of it is HTTPS, which is used in HTTPS. So HTTPS is when you visit a website securely. And TLS is the crypto that makes that happen. So HTTPS just says, here's the HTTP, and you're basically giving TLS the protocol or the crypto. TLS has different versions: SSL 2.0, 3.0, TLS 1.0, 1.1, 1.2, 1.3. This is where we are here, and 1.3 only has key agreement. The earlier ones, you had the choice. So actually all of the earlier ones you could choose between.
This one uses the
Key transport or key agreement. What changed? So TLS3 came out, it was standardized a couple years ago, and then 1.2 was standardized like, I don't know when, like maybe 15 or 20 years ago. So like why did people all of a sudden start caring a lot about key agreement? So basically there was a bunch of leaks about what the NSA were doing from Edward Snowden, and that more or less changed things. And so people said, cryptographers said, let's get rid of key transport. We now understand what the NSA's like plan is. We believe that they're storing all that information. And if the US government's doing it, then other countries are doing it as well. So you might say, who cares? It's the US, I trust them. That's fine. I already trust them for ICANN and all the other things that we talked about. But any country could be doing the same thing. Okay. Okay, so all of this built us up to this point where we now have a shared key. So Alice and Bob have a shared key. So now what I want to do is I want to build the tunnel assuming that we have the shared key. So step one was to get Alice and Bob the same key. So we solved that 2 ways. And now step 2 is, now that they have the same key, how can we get them talking securely? So once Alice and Bob share a secret K, they can transfer data. Just some terminology. This K value that we're talking about, we usually call it a master secret. And sometimes, more informally, we call it a session key. Basically, when I connect to Google and I talk to them, I'm using a session key or a master secret. And then once I disconnect and come back later, I'm going to negotiate a new key. Okay, I'm going to run that whole protocol again. I'm going to get a new key. So my key only lasts as long as the session itself. Okay, so now that we have shared symmetric keys, Alice has some data that she wants to send to the server, to Bob. How's she going to do it? What are the primitives that we can use now that we both of them know a symmetric key? So Alice knows K, Bob knows the same K value. And we have an adversary always present, always in the middle. And the adversary does not know K. I'll draw it kind of like that. Sorry, say it louder. Okay, so we can just encrypt it under K, right? Okay, is that enough? Depends what we're trying to achieve. So why? Give me a reason why it might or might not be enough.
Just encryption is not enough.
Okay, so that is true, but why?
You can, in
The
the
data
future,
can be
like you
altered.
said, you can get the session keys or whatever messages you're sending, and you can try your time to get that key.
Okay, so we can always try and break the K. We're not going to get away from that. So the best we can do is this perfect forward secrecy to establish the K. Then you still have the chance of brute forcing K. You can steal K. You can worry about maybe there's a weakness in the encryption algorithm that we don't know about today, but in 10 years we know about. In all those cases, you're going to get K anyways.
You can have a weak entropy also with your key.
Okay, sure. Anything else, though? So there could be a trust thing. We don't know who A is either. Like we know who B, A knows who B is, but B doesn't know who A is. So that's not what I'm thinking of. Okay, what are some other primitives that use symmetric keys? Is encryption's one, is there any others?
Signature.
So signature is public key, so it uses asymmetric keys.
Symmetric.
Is there, so symmetric key encryption corresponds to public key encryption, right? What corresponds to public key signatures, digital signatures? What's the symmetric key version of it? MACs, thank you. So message authentication code, okay? What does a MAC do?
It's just for the integrity.
Okay, so it stops, basically there's attacks like maybe Eve in the middle, she can't read it, she can't decrypt it, but she could change it. Okay, so if she can't change it, or if I don't want her to change it, then I'm going to put a MAC in there somewhere as well. Okay? Do I need it though? Why? It's already encrypted. What can Eve do? She can't read it, so she's going to go fiddle with it, but she's doing it blindly, right?
Because it provides integrity.
So it does. I agree. It provides integrity, but doesn't encryption too? I mean, I don't know what I'm doing. How's Avis? If she can't read the data, how's she able to change it?
Is it linked with the data size? Like if it's a big data, then like hash or keyed hash function like MAC can make the size smaller.
So it will. Okay. So a MAC will be a fixed length.
Yeah.
And so you'll be able to add something. You can add a MAC to this and it will be fixed length. So the hash, but you still, if Bob needs a copy of the data, he needs a ciphertext as big as the data. So it's something that you'll do in addition to it. So it doesn't compress the data at all. In fact, it makes it a little longer because you're adding this tag onto the end.
What about hashing?
So hashing is a way you can do MAC. So you can MAC with a simple hash. A simple MAC is just a hash of the key in the message. It doesn't work for technical reasons on older hash functions. When you zoom into the hash function, you see how it works inside. There's these things called length extension attacks. And so what people do is it's the same thing. They take the message with the key, they hash it, and then they take the hash of that and combine it with the key again, and then they hash it again. So that's called an HMAC. And then there's a bit of padding and stuff that goes into it. But basically you're hashing together keys and messages, to make a MAC. But I'm still not convinced I need it, because if it's encrypted, you can change it, but then it's just going to decrypt the garbage, right? That's a better way of putting it. So let's say say this is some piece of information, I want to change it to something else. But because it's crypted, it's all scrambled up. I see the scrambled up bit go across, so I can change it. There's nothing mechanically stopping me from going and changing those bits, right? But then when Bob goes to decrypt it, it's just going to screw up the ciphertext anyways, right?
Is this where SSL strip?
No, so that's something different, but yeah. Okay, so the answer to this question actually depends on how we do the encryption. Okay, so when you look inside how encryption works, what you'll realize is that encryption is structured, mainly because, let's say you're doing a block cipher, you're pulling in a block of data, you're encrypting it, then you're taking the next block of data, you're encrypting it, but then you're kind of mixing the two together because and then you go to the next one, and then you go to the next one, okay? And so the way that you pull it in, if it's structured, it is possible, even if I don't know what the data is, it's possible for me to tweak the ciphertext and actually know what that's going to do to the plain text,
Same as
okay?
AES?
Yeah, so it's AES, but the problem is AES just says, here's a block of data, 256 bits, here's an output ciphertext. But now I have data that's longer than 256 bits. So I have to call AES a couple times on each block, right? So we call that the mode of operation. So that's how you are going to chain together these things. And there are attacks where I can change ciphertext and I can predict what it's going to do to the plain text once it's encrypted, okay? So modes of operations have something called malleability. Okay, that means that you're able to change things and understand what those changes are going to do, okay? So I need my encryption either to be non-malleable or I need a MAC, okay? So those are the two options I have. A fancy way of saying non-malleable encryption is something that we've seen before, which is, we call it CCA secure. So CCA secure is non-malleable. So it basically, you can't get CCA security without having the equivalent of a MAC, whether it's explicit or implicit, okay? But we do have to add a random factor so that when you encrypt the same message twice, you get a different ciphertext. This is called an IV. This is not a secret, it's not a key. The IV is going to go along with the ciphertext. So Bob is going to get this IV value, and Bob is also going to then be able to use the IV value, and the adversary will see the IV value. There's nothing secret about it. It's just a random value that is used, kind of like a salt, okay? So CCA secure is fine. Or what we can do is we can do an encryption with a MAC. And in that case, what we need is a CCA security. We can have a less secure version, so we can have something called CPA, which is a weaker version. But then we need the MAC as well.
Doesn't the CCA secure also need a MAC?
So in order to achieve CCA security, you're going to have to be MACing or doing the equivalent of a MAC. Yeah?
But it's not exactly the same.
Yeah. Okay, can anyone tell me, let's say I want to do AES, but I said AES just does it 256 bits at a time. Okay, so what I need is I need a mode of operation. Does anyone know the name of a CCA secure AES thing? Say it loud. Okay, so GCM is an example. So Galois code, I forget what the M is. I was going to say code book, but it's something else. Anyways, yeah, so AES GCM counter mode, Galois counter mode. This basically does a MAC inside of it. I'm not going to go through the details of how the algorithm works. It's a little faster than doing this because when you do this, you have to, first off, you have to have the whole ciphertext. You can kind of encrypt it as you go, so you can kind of stream through it, but you're basically going to have to pass through it twice. You're going to have to encrypt it, and then you're going to have to MAC it. There's also subtle differences of do you encrypt and then MAC, or do you MAC then encrypt? And it does make a difference for complicated reasons. Actually, it has to do with the MAC itself. So, but anyways, I'm going to set those aside. Both of them have ways of doing it that is secure. So there is a secure way of MACing the ciphertext. So you get a ciphertext and then you get the MAC. Or what you can do is you can encrypt. You can take the plain text, MAC it, and then encrypt the whole thing. Okay. The one difference that's the biggest difference is that if the MAC is on the outside and the bits get flipped, you can detect it right away. You don't have to decrypt first. You can say you can throw it away right away because you can see it. But if you if you MAC first and then encrypt, you have to run the decryption before you realize that there's a problem with the MAC. Then and there's also like really subtle attacks based on timing. So what I'll do is I'll send something where the MAC inside is bad, and then I'll wait to see how long it takes you to realize that the MAC is bad, and that's going to leak some information to me. That's another kind of complicated attack. I'm going to show you at least one of these complicated attacks. So I'm going to show you one called Beast, and then this is going to be next lecture, but depending on how it goes, I might show you more, but I'll show you at least one of them. Okay, CPA secure. Does anyone know the name of one? So the most common one, the one that you'll see in TLS, is called CBC mode, or you'll see counter mode.
And this is less secure.
It's less secure, strictly less secure. Yeah, and so you need a MAC on top of it, and the MAC algorithm is usually called an HMAC, which stands for hashed MAC. It uses a hash function. Okay. Then there's a even worse encryption algorithm that I showed you. Remember the Linux Penguin, and you encrypted it and you could still see it. That's called ECB. ECB is not even CPA secure, so it's like less than CPA secure. Okay. So we don't use ECB at all. I don't think it's ever been part of TLS ever. And even if you MAC it up, it's still insecure. So you need at least CPA secure. Then you can. This construction, when you apply the MAC to it, the entire construction becomes CCA secure. Okay, so the encryption itself is only CPA secure, but MAC plus encryption is CCA secure. Or you can just use a mode of operation that's CCA secure out of the box. Another subtle point is here you just need one key. If you use GCM, you just have one key. Here you need two keys. So you need a symmetric key for encryption and a symmetric key for the MAC. How do you get two keys? So let's say we do key exchange. This gives me 1K. Okay, so let's say I want to use that for encryption, but now I need a key for MAC. Do I have to run this whole key exchange thing again? So that is one thing I could do. I could just run it again, okay? But that's expensive. Now I'm doing another 3-way kind of thing, or 2-way handshake. Is there something else I could do instead? So what I could do is I could take K, and instead of using it as a key, I could use it as a seed to a pseudo-random generator. Then I can blow it up to as many keys as I need. Okay? So that's what TLS will also do. Okay? So it will take K, and it will I'll just draw it here. So what I'll do is I'll take PRG, and I'm also extracting K if it was key agreement. If it's key transport, it's already random. I can skip the extractor step. But anyways, I take this, and then what I can do is I can generate as many keys as I want. And what you typically do in TLS is when Alice sends messages to Bob, she uses one key, and when Bob sends them back, he uses a different key. So they both are derived from the same thing, but messages flowing one way use one key, and the message flowing back uses the other. So what we end up with is we have a key for encryption for Alice to Bob. We have a key for encryption from Bob to Alice. And then if we're doing a Mac mode, then we have a key for Mac from Alice to Bob. And we have key for Mac from Bob to Alice. But we can skip this if we're using GCM. Okay, so that's what this gives us. So it gives us a set of 4 keys. And there's no problem. We can generate 1,000 keys. Like, it's secure. So it doesn't matter how many keys we generate. But so that's the output of this program. Okay, and then Bob will do the exact same thing. He'll generate the same set of 4 keys. And then we end up. Okay, then now we can basically put data back and forth, and it's that simple. Okay, we're done now. Okay, questions about this protocol?
Yes. Could you please explain again the malleability and non-malleability?
So save that for next class. So first off, to understand malleability, well, I'll tell you what the property is. CBC and CTR have that problem. They are malleable. What that means is even if I see CBC encrypted messages, I can start tweaking the ciphertext, and I can predict how it's going to tweak the plain text. So for example, with CBC, I have to think, I have to remember correctly, but it's something like this. It might not be exactly right. I can flip a single bit in the last block, and then when you decrypt it, that same bit will be flipped for you. Yeah, it's that kind of thing. Or I can flip a bit in the IV, and then the first block will flip the same bit, but then the rest of the blocks will be garbage or something like that. Yeah. And so when I show you the beast attack, I'll show you it's an attack specifically on CBC. So we'll draw out CBC, and then I'll show you one malleability attack. Yeah, that works. Okay, other questions? Okay, great. So next class I'll show you HTTPS, which is an application of this, and then we'll look at a couple of attacks at the crypto level on it. Okay, that's it. Thanks.